All right, the next topic, we already talked about how to use a semaphore to basically mediate access to some shared resources like Palantiri. Now we're going to see how to use a semaphore to coordinate interactions between threads, which is a different use case. This particular example is this ping-pong example. You can see it here. And basically what it does, it's kind of fun if you run it, it flashes in alternating sort of white on black and black on white, ping, pong, ping, pong. It also prints in a text window, pinging and ponging. And so what we have two threads. One's the ping thread, one's the pong thread, and they take turns going back and forth, printing ping and pong, like a ping pong game. This is kind of what it looks like. There's a whole bunch of different ways you can use this program, but one way you can do it is you can have a pair of semaphores, a ping semaphore and a pong semaphore, and we have a pair of threads, a ping thread and a pong thread, and they take turns going back and forth. So here's kind of what it looks like. The main program spawns the main thread spawns two other threads. So the ping pong thread object, this thing, goes ahead and spawns two threads, a ping thread and a pong thread, and then they alternate taking turns. So what's going to happen is this thread creates these other two threads by calling new, and then it starts them. And then, of course, as you've seen from assignment 1A, the run hook methods begin to run, so now they can do something. And the ping pong thread class implements this algorithm, and it's a very clever use of the gang of four template method pattern. And what's cool about this is that they both run exactly the same code, except the order of the semaphores is reversed in each of the threads. And you'll see why that matters in a second. This is what happens. The ping semaphore is initialized to the value of 1. The pong semaphore is initialized to the value of 0. So these are basically Java's counting semaphores being used in a restricted binary semaphore-like manner. Even though there aren't binary semaphores in Java, we can use a semaphore as a binary semaphore by simply having 0 or 1. And the count is initialized to not acquired for the ping semaphore, and it's initialized to acquired for the pong semaphore. And what that means, in essence, is ping will go before pong, which is exactly what you want to have happen. So now these two threads start to run. Here is the code that they run. They run a loop that basically says, for some number of iterations, let's say n, where n is 10, this thread is going to acquire, do some printing, and then release. This thread is going to acquire, do some printing, and release. And so this is actually what's built into the template method for both threads. Acquire, print, release. Acquire, print, release. Same thing. The way they differ is in this thread, which is the ping thread, this guy acquires the ping semaphore, does a print that says, ping 1 or whatever, and then releases the pong semaphore. In contrast, this thread acquires the pong semaphore, prints out pong in the count, and then releases the ping semaphore. Well, as you saw before, we started with the ping semaphore available and the pong semaphore not available, or acquired, not acquired and acquired. And so the way this is going to work is the ping thread, whichever of these, if both threads start up at the same time, which they will, only the ping thread can go first because the ping semaphore has a count of 1, whereas the pong semaphore has a count of 0. So this guy will block right off the bat, whereas this guy will acquire, print, and release. And what's interesting about this example is it's a good example of non-fully bracketed acquire and release protocol. Because the thread that acquires the semaphore is not the thread that releases it. It's the other thread that releases it, and they just take turns going back and forth. So it's a really cool example that it demonstrates a whole gaggle of patterns. We got template method pattern, of course, to alternate pinging and ponging in a very clean and conventional pattern-oriented way. We have got the use, of course, of the bridge pattern, which is what the semaphore uses under the hood to have fair and non-fair semantics. We've got a couple threads running around. It's just a fun, really neat example that's really clean. And as you can see here, the way this works is we have these semaphores, mine and other. Each thing has something called mine and other, and we simply initialize them to be in the reverse of each other. So acquire says mine acquire, so I acquire my semaphore, and when I'm done, I release the other semaphore. And again, you'll have to block if your semaphore is in use. When you're done, you release the other guy's semaphore, and that's how they take turns. And then finally, the play ping-pong thread, after it starts these other threads to do their pinging and ponging, it sits there in a loop joining with these other threads. So as these other threads finish their iterations, then the main thread will pick up the results and only proceed after the other threads are done. So that's a classic example of a barrier synchronizer. Okay, so that's basically the end of the example showing how to coordinate thread interactions by using semaphores in a non-fully bracketed